Okay, good morning. We're going to be going on to section 11.3 today, and the objective for this section is to use ratios to find areas of similar figures. So if you remember, a ratio is going to compare two things, and similar figures they have the same congruent angles, but they have proportional side lengths. And if you remember, we studied similar figures all through chapter 6, like the whole chapter. Okay, so we're going to hop down to this theorem box here. It says if two polygons are similar with the lengths of corresponding sides in the ratio of A to B, then their ratio of their areas is going to be A squared to B squared. Okay, so excuse me. You might remember when we were comparing perimeters, the perimeters are going to have the exact same ratio as the sides. But to get the area ratio, once you simplify that ratio, you have to square both numbers, which kind of makes sense when you think about area because our units are always squared. So if you look at this picture, it says in the diagram, triangle ABC is similar to DEF. So remember, that tells us A is congruent to D, B is congruent to E, C is congruent to F, and then all my sides are proportional. So I know that side BC, right here, is proportional to EF. And if you look over here on our picture, they gave us BC and they gave us EF. So if it says ratio of ABC to DEF, remember order matters. So I'm going to take the 8 first and then the 12. And then you're just going to reduce. So reduce by 4, and we get 2 to 3. This is the side ratio. It's also the perimeter ratio. But down here it says find the ratio of the areas of these two triangles. So it's going to be 2 squared to 3 squared, and the ratio of their areas will be 4 to 9. You want to make sure you reduce this first before you square it, or you're gonna get some crazy numbers. Okay, so in this one, figure 1 is similar to figure 2. Find the indicator ratio, the ratio of their perimeters. Remember, it's the same as the side ratio. Okay, so 1 to 2. So I have the 18 on the 1 and the 10 on the 2. I'm going to reduce that by 2, and I'm going to get 9 to 5. That's my perimeter ratio. To get my area ratio, I'm going to do 9 squared over 5 squared. It's going to give me 81 over 25. Okay, that's page 1. This is kind of a really quick lesson today, so hopefully that'll be a nice little break. Okay, you're installing the same carpet in a bedroom and an office. So here's the office in the house, here's the bedroom in the house. The floors of the rooms are similar. So there you go. It's telling you they're similar. The carpet for the bedroom costs $225. Sometimes I like to just write those numbers in the box. Carpet is sold by the square foot. So that right there is telling you we're talking about area. Square foot. If you think about carpet, that's going to be area. How much does it cost to carpet the office? So we need to compare the areas to the cost here. Okay, so it doesn't really matter which way you work. I'm going to go office to bedroom. Okay, so if I write my ratio office to bedroom, reduce that by 2, I get 7 to 5. Now, this 7 over 5 will compare the sides and it'll compare the perimeters, but I'm not comparing those. I'm comparing the area. Okay, so you got to square these to get your area ratio. So 49 is to 25 as I don't know the cost for the office. X is to 225. Hopefully that makes sense to you. And then you're just going to cross multiply. So you're going to get 25 times X equals 225 times 49. And then you're going to divide both sides by 25 to come up with the cost. So we've got 225 times 49 divided by 25, and you should have $441. Okay, the other thing you always want to make, check to make sense, check to make sure that the answer makes sense. So the bedroom is smaller, is $225. The office is bigger, that's $441. That's pretty accurate. And when you're grown, you might be figuring this out for your house. I've had to do that before. When you go shopping at Lowe's or Home Depot. Okay, a large rectangular baking pan is 15 inches long and 20 inches wide. So I'm gonna just label this large and 15 inches long and 10 inches wide. A smaller pan is similar, so there's that word again. And the area of the smaller, so we don't really know what it is, but we know it's smaller, okay? Its area is 96 inches squared, and they want us to find the width. Okay, so since we're going to be comparing areas, we need two things. We need the area ratio, and since we want to find W, we're going to be looking at 10 compared to W, but not just 10 and W, because it's area. So it's going to be 10 squared is to W squared as... Then we need the area of this. Now, they didn't give it to us, so it's very easy to find in a rectangle. Okay, so length times width or base times height. So this is going to be 150 inches squared is going to be this area. So 10 squared is to W squared as 150 is to 96. And then again, you're just going to cross multiply. So 150 W squared is equal to 9,600. So 9,600 divided by 150 is 64. So W squared is 64. So the width of your smaller pan would have been 8 inches. Oops, sorry. I didn't realize that you couldn't see any of that. Sorry about that. You're just square rooting both sides here to get the 8. All right, last one. The Pentagon in Washington, D.C. is a regular pentagon. If you remember regular, all sides, all angles congruent. Each side of the base is about 900 feet, and the area is about 1,400,000 feet. So this is Washington, D.C.'s Pentagon. You got the base to be 900 feet, and the area is 1,400,000 feet squared. Okay, you have a scale model of the Pentagon, so our little scale model at home. Okay, where the perimeter, so different word, is 30. So perimeter is 30 yards. So if you notice, we got feet, we've got yards, we've got area, and we've got perimeter. Find the area of the base model to the nearest square yard. So this one gets a little tricky. Okay, to find the area, we need to have the area scale factor. So first, we're going to take this perimeter of 30. We're going to divide it by 5 because there are 5 congruent sides here. So this is going to be 6 yards. Okay, and you kind of have some options here as to how you want to go about that. There's just different, I mean, you could put it all in feet and then convert back, or you could start converting to yards right now. It's kind of up to you. So I might just switch over to yards. So there's 3 feet in every yard. So I'm just going to take this 900 divided by 3. That's going to give me 300 yards per side here. And then I'm going to get my area ratio by doing 300 is to 6. So that's going to be 50 is to 1, but I have to square them because it's area. So it's going to be 2,500 is to 1 as, now here's a problem. This is in feet squared, and this is where it gets tricky. We know this is our unknown. We want it to come out in yards squared, so we have to convert this feet squared. And you can't just do, there's 3 feet in a yard. You can't do that, okay? So if you think about like a rectangle, let's think about this, right? And if it was 3 feet by 3 feet, okay, you got to think about how many feet squared that is. So this is 3 feet by 3 feet is going to be 9 feet squared equals 1 yard by 1 yard, which is 1 yard squared. So when you do the conversion on this, 1,400,000 is to 1, so this is feet squared, times 1 yard squared, which is what we want, over 9 feet squared as your conversion. So I'm just going to take 1,400,000 and divide it by 9. And it's going to give me a decimal. And you can round that off, sorry. 155,555.6, let's say. And then you're just going to cross multiply. So it's going to be 2,500x equals 155,555.6, and then divide that by 2,500. And we end up with 62.2 yards squared. Whoops, sorry. This is a good critical thinking problem. Don't sweat it too much. If you were a little lost in there, maybe rewind it, pause it to just see how I changed up the units. But I don't think you'll have anything too crazy. All right.